Alrighty, this video is focused pretty much entirely on binary search, so how that works. And I've got a bunch of different, not necessarily variables up here, but tracking different pieces of information um, about the search and the list and what's going on, such that you can use this information and anything else that occurs to you, because this list is not intended to be all inclusive. You may have other things that you think about when you look through this problem that you're like, hey, we could track this. We could use this piece of information in figuring out what to do next, and that's perfectly acceptable. You don't have to be using the same information that I have here. There's more than one way to skin a cat. In fact, just to point out, this algorithm can be implemented iteratively, or it can be done recursively. So anyway, we're just going to kind of run through visually at a high level what changes look like they're happening with the list and this information that we've sort of collected about what's going on. So the way that your algorithm is going to work, and this is just part of the fact that we're using an array of integers. We wouldn't have to necessarily use an array to contain our list. So that just means that some of the artifacts that we're using up here, such as an index, wouldn't necessarily be applicable to some other kind of data type, and instead you'd have other attributes that you'd be using to sort of keep track of what's happening as you step through the algorithm. But what we will do down here in BlueJ is just kind of give some high-level pseudocode for how the search goes. And we wouldn't necessarily have to do all of this in exactly the same order. Some things could be before other things or after other things, but this is just how I'm presenting it. So we're going to have an initial point, pick an initial point roughly, gosh darn it, halfway into the list. And exactly how you determine what is roughly halfway is going to be up to you. I mean, there's different pieces of information that could be used, but regardless of what technique you're using, there's going to be times where half is, an integer and half. That would be something similar to when I went through bubble sort and was trying different things. Something didn't work. I made some changes, tried it again, things improved. So you may have to play around with exactly how you're figuring out what halfway is. But we pick an initial point roughly halfway into the list. Then we're going to determine if value is target value. And we'll just say yes, search complete. At which point we don't have to continue going through the list. No. Found value is higher. So search value is lower. And we'll just change this up here just so we're clear. And we'll also say, oops. So here we're just going to be looking at this. This will represent what value we've actually plucked out in the list, right? So 8 for index 3, 9 for index 4, what value do we have? And we're just leaving these question marks for the moment because we haven't really jumped into running through the algorithm just yet. We're just writing down some steps. It just helps keep track of what's going to happen and whatnot. And then we have no found value is lower, search value is higher. And then in addition to the no's, we would then have search again in list. And here we're really kind of jumping back up to the top, except our starting list, or the amount of the list that we can work with when we go to perform a search, has reduced in some form or fashion. So eventually we're going to eliminate the search space within our list. So we'll either find the value that we're looking for, or we will have knocked out enough numbers that we know it can't be there anymore. So anyhow, let's just say that we're looking for 40, right? So we're just going to pick a value that we know is in our list, and we'll just see what happens. So we have a current lowest index at the very beginning. If we took, let's say, half of our maximum possible index at the moment, like 0, like 15 minus 0 is 15, and we cut that in half, we get 7.5. So if we round it up, then we would start at 8. So we'll say that our current index is 8. Search value is 40. Okay, so this is kind of, our initial rough way into the list. We haven't really evaluated anything yet. So now we figure out, is 40 higher or lower than 20? Now our list value here, we get 20. So 40 is larger than 20, which means we're going to be needing to move to a higher index in the list. So once we've made this evaluation, we could do things like say our lowest valid index is now 8. Our highest index hasn't changed, and we've effectively eliminated all of these blocks out of the list. So our list is now essentially cut in half, right? We'll never go below 8 because 40 was larger than 20, so there's no value over here that could possibly give us the correct answer. So we've looked for our search, so we didn't find it yet. No, it is higher, so we're going to search again in the list. So just like we had to pick an initial point roughly halfway into the list, now we're using the list that is left. So we have to choose something between 8 and 15, and we'll be performing a search here. So the reason that I didn't count the initial pick of the middle of the list as a search is from the perspective that had our list only had one element in it, it would either have been the answer or not. We never actually had to search for it. So the answer to the problem was immediately evident, and we would just be done right there. There wouldn't actually be any searching. So it's not until we need to look outside of that we've started to perform a search. So anyhow, we have 7 and 15. So conceptually, our list length, and this is something that I did in class, and I guess I'll do again here. So our remaining list. We'll just say that. Has now really dropped, we'll just say that we cut it cleanly in half, even though technically we might not have, but we now know that there's really half the list left to look at. So if you'll just notice that when we jumped in and we happened to use 8, not that we had to use exactly 8, but 8 was half of the length of the list, and now we're down to 8. So if we looked at, let's say 15 minus 8, well, that equals 7. So if we round it up again, then that would be 4. 4 in addition to 8, which would give us 12. So we'll say that our current index is going to be 12. So we come to 12, our list value is 37, and now we need to perform our evaluation down here. So 37 is lower than 40. So we haven't completed our search, so the value is lower, so we're going to be looking to higher indices again. So just like we did before, we can now say that our lowest valid index is 12. Search current index. Okay, so now we're here, and we have effectively, cut the list in half again. So now we're down to 4. We're going to have to do another search, and now we need to figure out, where between 12 and 15 we're going to look. So if we just did, 15 minus 12, that's 3. If you round it up again, that's 2. So if we added 2 onto 12, that would be 14, which would give us 40. So now we've seen that we've found our answer. So search is now true, and our, whoops, forgot to change our current index. So our current index would be 14. So this now becomes our answer, right? It's 14. So we performed 2 searches out of 16 objects and found our target value. So what you would find out of any binary search algorithm is that you're never going to perform more searches than log base 2 of the initial length of your list. And I think that I can kind of show that a little easier using something else, but basically, okay. So we're back at our list. We've currently evaluated. We've gone through one possible search in which we found the value of 40, but let's run through it again with a different value, something that we won't find, just to show you how that should look. So let's say we want to look for 10, because that is not in our list. Let's run through it and just see what happens. So if we start at index 8, our list value is 20. So we do an evaluation. 10 is less than 20, so that means that we're going to be looking at lower indices, and we have essentially eliminated everything higher. So we'll say that our highest index is now 8. Our remaining list is now effectively cut in half to 8. We will be performing another search. And so now we're looking somewhere between 0 and 8. I think it's pretty clear that we'll just go ahead and choose 4. So that makes our current index to 4, and here we have a list value of 9. you'll see that now we have to do an evaluation. 9 is smaller than 10, so that means we're going to be going to higher indices. So we've eliminated 0 through 3 as valid indices. So our lowest possible index was 4. Our highest is still 8. We're going to have to perform yet another search. And we've now conceptually cut our list down to 4 elements. So somewhere between 4 and 8, I think we might choose 6. So our current index is going to change to 6. We have a list value of 14. Okay, so now we need to evaluate 10 versus 14. So 10 is less than 14. So we still have something left that we could search. So we're going to perform yet another search, which results in our effective list now only being 2 elements. Our highest possible index is now 6. So as you can see here, we're gradually converging on that, and this is converging towards 1. So between 4 and 6 would be 5. So our current index becomes 5. Our list value becomes 12. And once again, we evaluate 10 is smaller than 12. So we haven't completed our search. The value is lower. We would need to try to search again, except we don't have any search space available. So at the point that we've done this, we know that our highest valid index became 5, and if we were to go down, well, then we would just be going back to 4, which we've already visited. So this is an interesting point, just to illustrate that how we choose whether or not we bounce gets a little strange. Because at this point, if we used the kind of math we were using before, which is to say our highest index minus our lowest index, rounding up, we would actually jump again, right? We would determine that we would jump to the left by 1, which isn't the end of the world. We would just reevaluate index 4 again, and then our highest index and our lowest index become exactly the same, and we have no space left in our list. So anyway, in this case, we haven't found the answer, but per my point earlier in showing, as we effectively cut the list in half again and again and again, it doesn't take us that many searches, right? We didn't go more than 4. You could say at most we went 4, right? As we went from 8 to 4 to 6 to 5, and then back to 4, right? So the first one didn't really count because it was our starting point. So at most we went 4, and log base 2 of 16 is in fact 4. So we're guaranteed that we will exhaust our search space after 4 searches. In this case, we didn't find the value, and the answer is -1.